Hello everybody, welcome to chapter 1.5 and we're going to talk about infinite limits. We're going to be able to determine infinite limits separately from the left and from the right, and we're also going to find and sketch vertical asymptotes of the graph of a function. Alright, let's get started. So, the first thing that we should do is go over an example like this. So say that we had the function, let's consider the function f of x equals 3 over x minus 2. And what we're going to do right now is we're going to look at our table. Give me 1 minute. We can look at this numerically first. We can look at the table of this function. Let's get our y equals going. So in our y equals, clear out whatever you might have in there, and then we're going to put in second alpha. We're going to do 3 over x minus 2. And then we're going to press second, and then we're going to look at our table. So we're going to press second window to get our table set. Oh, second window. And as you can tell from the bottom, if we had a positive 2 in there, that would make the bottom 0, which is an interesting thing. So we're going to start by looking at 2, and we're going to look at small changes in our graph. Now we're going to press second graph to get into our table, and look at that. That's pretty crazy. Here's 2. Oh, let me go down one more. There we go. Here is our 2, and we don't have a value there, which makes sense because we can't have 0 on the bottom. But as we get close to it from the left and from the right, we can see some pretty big numbers. If we made our change in x even smaller, and you can do that by pressing the plus and then making it even smaller, so let's like add another 0 or 2 in here. And then press enter. Check it out. Oh, we have to do our table set again, so do second window, start at 2 this time, and now press second graph. There's 2. Wow, those are some really big numbers, and we made the change in x really small. We get really big numbers as we get close to it. So we can see that we're approaching, oh, let me do that again. We can see that we're approaching really big negative numbers from the left and really big positive numbers from the right. And so, here's what we can say. Now that we've looked at it numerically, we can say, as x approaches 2 from the left, and we can just say of f of x, we would get negative infinity. And a limit as x approaches 2 from the right of f of x, we would get positive infinity. And again, this wouldn't be sufficient enough. If you were trying to prove something numerically, you would have to write out the table. But for the sake of time, I'm not going to write out the table because I already showed it to you. And next to this, I want you to write a bracket, and we're going to talk about the concept of an infinite limit. And all that means is that it's a limit that decreases or increases. And here's the important part, without bound. Without bound, just think of that either means negative infinity or positive infinity. And it does that as x approaches c. So a limit that decreases or increases without bound as x, let's write the word as, how about that, as x approaches c. Alright, next topic, determining infinite limits, let's say from a graph. And it's also important to see, to to talk about. We'll go over it in just a second, but these infinite limits are vertical asymptotes. That's how they appear on a graph, is as a vertical asymptote. So if we look at the first function, let's say we had an f of x equals a 1 over an x minus, pardon me, that's a 1, an x minus 1 squared. And if we threw that in our grapher, here would be positive 1, and it would be doing sort of this. Let's draw some dotted lines. Okay. It would be doing this. And it would be doing this. It'd be increasing to positive infinity from both sides. If we had another function, let's consider negative 1 over x minus 1. This is another example of a graph increasing or decreasing without bound, and here's what this would look like. At 1, again here this was 1, and this is 1 again, I'll call this one like 2 just so we know what that is. And let's call this one 2. Our graph would sort of be doing this. Here's 1 dotted line, and it would cross through here, and it would go all the way up. And on the other side, it would go all the way down. Okay, so if we were to graph these right off the bat, we would see this behavior, and we would understand, okay, at x equals 1 for both of these, there's infinite limits. All right, that makes sense. And what we can also tell about these graphs right away is that they both have vertical asymptotes at x equals 1. So let's make sure we identify that. And let's also identify the limit as x approaches 1, we'll say from the left for f of x, that's positive infinity. The limit as x approaches 1 from the right for f of x is also positive infinity. That makes sense because our values approach positive infinity as we go in for both directions. For g of x, it looks a little bit different. We have the limit as x approaches 1 from the left, and we can see that's going up without bound. That means positive infinity. The limit as x approaches 1 from the right, however, goes all the way down without bound. So we call that one negative infinity. And again, we can tell that from the graph. So nothing very tough to see about that. Let's talk about it analytically, though. First, let's talk about the first function. So, f of x. The limit as x approaches 1 for f of x for 1 over x minus 1 squared. Here's what's going to happen. As we get really close to 1, right? So I'm going to write out two scenarios. So as we approach 1 from the left and as we approach 1 from the right, here's an example of what might happen. We would have, say, maybe 1 over like 0.999 minus 1 squared. I'm just going to draw a little arrow. Okay. And over here, as we're approaching from the right, for f of x, we might have, for example, the number 1.002 minus 1 squared, right? And if you plug this exact thing into your calculator, you guys, or if you just looked at your table, you would see that we get like a crazy small number on the bottom. So we could get 0.5 zeros, 1, 2, 3, 4, 5, 1, and from the right we would get 0.1, 2, 3, 4, 5 zeros and then a 4. And in case you don't have the behavior memorized, just know that whenever you have a really tiny, tiny number on the bottom of a fraction, that makes this whole thing huge. So since we have such a small, small number here on the bottom, these just become really, really, really big numbers. Like this one is actually, I think, 1,000,000. Yeah, this one's 1,000,000. And this one's, wow, 2,000,000. I might be messing up a 0 there, but that's not my point. The exact number isn't my point. The point is that it gets really, really, really big. And so, since we approached the left and the right and we got really close, we can say, again, that the limit as x approaches 1, in general, for f of x, is positive infinity. These are both really, really, really big numbers. For g of x, let's start to just kind of visualize that, right? The limit as x approaches 1 from -1 over x minus 1. Let's just talk about this for a second. If I were to plug in, let's see, if I were to go from the left, if I were to approach 1 from the left for g of x, here's what would happen. I'm just going to write it out. The bottom, our denominator, would be a small, I'm going to underline small because it would be a small, negative number. But hey, so would the top. The top's also negative. Top is also negative. I'm going to say neg for short. So when that happens, we're still going to have that huge number, just like we had here. If we have a really small number on bottom, we're always going to have a huge number. But since we have a negative over a negative, we could conclude that coming in from the left, for g of x, we'd go to positive infinity. From the right, the bottom would be a small, and again, I'm going to underline the word small here because it would be really small. Pardon me, positive number, but the top is still negative. So we have the opposite case. Because we'd have a positive small number on the bottom and a top negative number, that would make the entire thing negative. So we'd still have that huge number, but because the top is negative, it would be now going to negative infinity. Okay. That's just a discussion I wanted to have. Let's move on to vertical asymptotes. I'm sorry if you can hear the pen hitting the camera. Working on getting a better camera situation. So just hang tight for that. Okay. Vertical asymptote. So first let's define it. It's always good to have our formal definitions going. So for example, if, let's do a fancy f of x approaches infinity or negative infinity as x approaches c from the right or the left, comma, then the line x equals c is a vertical asymptote of the graph f. You can use a little fancy f. So let's do some examples of finding these. And you'll also notice before we go into defining them that whenever you have a vertical asymptote, none of the conditions of continuity are met. That's why a graph is discontinuous wherever it has an asymptote. All right, so next topic is finding VAs. Pardon my abbreviation. All right, so say for example, we had the function f of x equals 1 over 2 outside x plus 1. Now you were asked to find the vertical asymptote. Here's how we could do that. You could just visualize that you would subtract 1 here, and then that would get 0, and we have 2 times 0. That's great. If you're good at math and you're just like super fast at algebra, good for you. Here's another way to do it if it's harder for you to conceptualize. We know we need the bottom to be 0, so set this whole thing equal to 0. We'd have 2x plus 2 if we distributed. We make it equal to 0. 2x equals negative 2, x equals negative 1. All right, and if we plugged that in to, oh, did I just say plug in? Don't do that. If I substituted in negative 1 to my f of x, here's what I would get. I would get 1 over 2 or 1 over 2 times 0 or 1 over 0. And here's the following things we need to have if we're going to have a vertical asymptote. We need to have a 0 on bottom, and we do. And we need to not have indeterminate form. We can't have a 0 on top as well, and we don't. We have a 1. So we know we have a vertical asymptote when x equals negative 1. You can also say we have non-removable discontinuity at x equals negative 1. Both are true. Awesome. Next example. Say we had the function f of x equals x squared plus 1 all over x squared minus 1. Well, you guys are pros at this limit finding by now, that you understand it's important for us to factor out and divide out any possible... Oh wait, that's the next example. Pardon me, forget that I said that. But again, to find an asymptote here, what we could do is just set this bottom piece equal to 0. So if we had x squared minus 1 equals 0, and we factored that, we would really have x plus 1, x minus 1 equal to 0. We do some mental math. We know from the zero product property we could just set each of these equal to 0. We would have to subtract 1 here. We'd have to add 1 here. So here our x would equal negative 1. Here our x would equal positive 1. And here's what happens if we plug those numbers into our original f of x. For negative 1, I would get 1 plus 1 over, oh, I forgot my squared. Don't forget your squared. 1 minus 1, which would be 2 over 0. And again, the conditions are met. We have 0 on the bottom. We did not get indeterminate form, so we know for sure we have a VA, vertical asymptote, oh, pardon me, colon, vertical asymptote at x equals negative 1. If we plug in 1, we get, again, 1 plus 1 over 1 minus 1 because we have the squareds, right? It didn't matter that this was negative because we squared it, we made it positive anyway. So these two are going to be the same thing when we plug it in. Oh, when we substitute it in, pardon me. And we get 2 over 0 again. So again, we have proved that we're going to get a vertical asymptote here as well at x equals positive 1. And remember, it's important that you analyze this more than one way. This is a great analytical way to find this, a good way to check and, what am I thinking of? Confirm what you found analytically, graph this. And it should show at x equals negative 1 and x equals 1 vertical asymptotes. All right, moving on to our next example. So say that we had the function g of x and we're still finding those. Oh, pardon me, we need an equal sign in there. Let's start that over. g of x equals 5x squared all over x minus 2, and we're still finding asymptotes. Again, remember, set the bottom equal to 0. Here we can just kind of mental math do that. If we set this equal to 0, we'd have to add 2. So we know when x would equal 2, we'd get the following if we substituted it in. And here we would get 5 times 4, which would be 20 over 0. Great. That proves that we would have a vertical asymptote at x equals 2. Not so bad. Set that bottom part equals 0 if you have a hard time looking at it that way. Let's confirm this graphically, like I was saying. Let's get used to doing this in more than one way. So let's grab our calculator, and let's see if we truly do have a vertical asymptote at x equals 2. So, second quit, I'm going to go to y equals. I'm going to clear out what I had before. I'm going to do alpha y equals, get my fraction going. I'm going to have 5x squared, and I'm going to have x minus 2. I'm going to first just graph it just to see what it looks like. You know, and it looks like I'm zoomed in pretty close. So let's try fixing that. Let's press zoom, and let's go to Z standard. Let's press 6. There we go. That's a lot easier for me to see. If I look here, here's 2, and it looks like my graph is starting to go down, all the way down. So it does look like there's an asymptote. Let's double check though. Let's look at our table. So we'll press second window. Let's start really close to 2. That sounds good enough to me. Let's make our change in table though something not so crazy. Oh, quit. Let's do that again. Second window. Let's start again really close to 2. So let's do like 1.999. That's fine. And let's make our change 0.001. Now let's press second graph to look at that table. Okay, and there we go. We can see that in fact there is that asymptote at 2. There's an error message in there, which means we have that discontinuity that we were looking for. Okay, that makes sense. All right, we're going to quit out of that. And we're going to do our next example. Love these examples. So say that we had f of x equals x squared plus 2x minus 8 all over x squared minus 4. And then we're going to say that equals x plus 4, x minus 2, x plus 2, x minus 2. That's just factoring, right? It's typically a good idea to factor if you can, so you can divide out anything that's common. What we can see here is that our x minus 2's would cancel, and we are going to get x plus 4 over x plus 2, but we need to note that x is not equal to 2. Here's the thing that is very important for you to understand. This x is not equal to 2. What that means is that we have removable discontinuity when x equals 2, or we have a hole. This does not mean that we have an asymptote at 2. We do not. We can plug 2. Oh, goodness gracious. I keep saying it. I'm so used to it. All right, we can substitute in positive 2 to this function, and we would not get 0 on the bottom, so we would not get an asymptote. However, because of the restrictions of our original function, we would get a hole. We could get something that we're not supposed to get, or we would get something that would be undefined, pardon me. So we have removable discontinuity at x equals 2, but our asymptote is not at 2. If we take x plus 4 over x plus 2 and we set this bottom equal to 0, then we could see that we would have a vertical asymptote at x equals -2, because if we plugged that in, we would get, oh goodness, if we substituted that in, we would get a 0 on the bottom, and we would get a +2 on the top, which would tell us that that is an asymptote. So we can say a vertical asymptote of x equals -2. We could also say non-removable discontinuity. I'm going to say at x equals -2. And here's an example of the graph. So say that we had, oh, I made that in the wrong direction. That's okay. Here, let's call this one 2. Let's call this one -2. Let's call this one -4. And let's call this guy 2. All right. We've labeled our graph, which is very important to do. We know we're going to have that asymptote here at x equals -2, so let's draw that dotted line. And here's what our graph's going to be doing. It's going to come in, and it's going to cross over 2, but then we're going to stop, we're going to do a little hole, and when x equals 2, we have that hole, we have that removable discontinuity. And yours shouldn't like flatten out like mine, it should kind of go a little bit down. I'm not a perfect graph drawer, I apologize. But from the other side, we would cross over at 4, and we would just swoop down to -infinity. So we can see that the limit of f of x as x approaches -2 from the left, clearly we can see that that's going to be -infinity. But let's talk about y for a second. On the bottom of this fraction, if I plugged in a number that was really close to -2 from the left, right? So that would be something like -2.00001, right? A -2.001 plus a 2 would be a really tiny negative number. And on the top, the 4 would cancel it out. I'd have a positive. I'd have a positive over a really small negative number, which means I would have that negative huge number, -infinity. The limit as x approaches -2 from the right, however, for f of x, clearly we can see is going to be +infinity. But again, let's just talk about analytically why. If I were to plug in a very small number close to -2 from the right, that would be something like -1.99999, right? And since 2 is bigger than that, that would be a positive number on the bottom, very small and positive, and I have a positive on top. A positive over a positive would get me a positive, and I'd have that really tiny number on bottom, so that's what would make the huge infinite answer as I get closer and closer to 2 from the right. All right, moving on. So let's do a last example for you all. Say that we had the function f of x equals x squared plus x minus 6 all over x squared plus 4x plus 3. You guessed it, it's always a good idea to factor whenever you can. So we're going to factor this out. We're going to get x plus 3, x minus 2, x plus 3, x plus 1. And we know we can cross these out, and we get the new and improved f of x, which is x minus 2 over x plus 1, but we have to pay attention to our essential restrictions, which would have also been that x cannot equal 3. Oh, pardon me, -3. There we go. x can't equal negative 3, because if I substituted that in here, I'd get a 0, and then that would cancel out the bottom and get a 0, and I can't do that. So, again, it's very important that you realize this. X not equal to negative 3, that is not an asymptote. At negative 3, what I have is a hole. I'm going to write that right here. We're going to have a hole, or removable discontinuity at x equals negative 3. That's all we've found so far. We have not found an asymptote. What we need to understand about this new function is what will make the bottom of it 0. And again, you could do that whole thing that I showed you before. Set this x plus 1 equals 0. You subtract 1, and you get x equals negative 1. So we have a hole or removable discontinuity at x equals negative 3. But we have a vertical asymptote or non-removable discontinuity at x equals negative 1. So two separate things are happening in our graph. Both are discontinuity, but they're going to look different when we graph it. Before we graph it, though, I would like to talk to you guys again about the analytical situation, about what's going on here. So let's talk about the limit as we approach that negative 1. Let's start with from the left of f of x. Let's just picture this. That means that we would have an x minus 2 over an x plus 1. And imagine that this x gets very, 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 very small. Or pardon me, not very small yet, but it gets very, very close to negative 1 from the left. So an example of that might be substituting in something like negative 1.0001 plus 1. And then if we had negative 1.0001 minus 2 on top, right? Just kind of imagine what's going on here. I'm not going to do the math here, but what we can see is that because the difference here would be negative, we'd have a very, very, very small negative number on bottom. On top, we would also have a negative number. So if we had a negative over a very, 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 very small negative, we would get that huge positive number. We would get positive infinity. Again, negative number on top, very, 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 very small negative on bottom equals huge positive number. Negative over negative is positive. Conversely, as x approaches negative 1 from the right for f of x, again, imagine, let's just write it out. So if we had x minus 2 over x plus 1, and we imagine those values in there. So let's substitute in something that's close to negative 1 from the right. That could be like negative 0.999, then continuous. I don't know, whatever you want to write on from there. And then on the bottom, same thing, negative 0.999. You could write out a bunch more nines if you truly want to, whatever pleases you. But you get the point. Very, very close to negative 1 from the right. Now, let's imagine what's going to happen here. Let's not plug this into our calculators. Let's just think about this conceptually. Here, since 1 is a bigger number than this would be a positive on the bottom. And it would be really, really, really small. On the top, however, we still got the negative situation going on. A negative minus something, it's always going to be a negative answer. So if we have that negative and a really, really small, small positive on the bottom, we all know a negative divided by a positive, that's negative. And since we have that really, really tiny, tiny number on the bottom, we have a huge answer as our results. We have the negative infinity. And when we graph this to confirm our analytical observations, here's what we get. So let's call this guy 2. Let's call this guy 2. -2. And let's go out here to -3. All right. And as we observed, we know we're going to have that -1 asymptote vertical. And we're going to have the hole at -3. So let's graph this all out. We would cross here at x equals 2. And we cross the y at y equals -2. And we start to go all the way down. Which makes sense because as x approaches -1 from the right, we got -infinity. Cool, we were right. And as we come in from the left, we get really close to that x-axis. We have that hole at -3. We have that removable discontinuity at 3. And then we get close to -1 and we just shoot straight up. Which again, makes sense given our observation analytically. As we approach -1 from the left, we can see that we get positive infinity, those huge values. Okay, that is all I have to show you about finding infinite limits and vertical asymptotes, and we'll see you in class tomorrow.